This is Brian Finley with the Lenovo Big Data Center of Competency. Today, we'll be doing a Big Data Solutions overview. Let's get started. We'll be covering what is big data, what does it really mean. We'll be talking about big data software, all of the pieces that go together to make for a big data solution. We'll talk about the kinds of hardware that is appropriate for running a big data cluster. And then we'll discuss Lenovo Big Data offerings. So what is big data, really? Big data is when you're dealing with a collection of data sets that are particularly large or particularly complex, such that it makes it difficult for you to process them in the way that you would classically handle your data, either from a storage perspective, a data movement perspective, or an analytics perspective. There are many different softwares that make up a full big data solution, and Hadoop and Spark are key components that are frameworks, if you will, that allow for integrating other applications and giving them access to all of the resources within the big data solution as a whole. What makes data big data? So lots of people will talk about V's. Some people will refer to the 3 V's. Some people will talk about 4 or even 5 V's, but I think that 3 V's is sufficient to really give a good perspective. So first, there's velocity. There's lots of data coming in, and it's useful if we have a way to handle it and analyze it to make better informed decisions. Velocity. It's coming in very quickly. The faster you can process it, the better of an edge you can get on your competition, and more effectively you can engage your customer base. And then there's variety. There's lots of different kinds of data. In the old days, the way that data got into a company's computer systems was through data entry. We even had a job description that was a data entry clerk. And the data that they would enter was input through a form, or at least a spreadsheet, that was what you would call very well structured data. In order for you to hit enter to save the data that you'd entered, it had to pass a validation check. Certain fields had to have just exactly the right number of characters. Certain fields couldn't have commas. All kinds of rules around the data that would make it very well or highly structured data. Also, because it was being typed in manually by people, the volume of data was inherently limited. But if we look at the kinds of data that we have coming into our systems today, we have a lot of it that is unstructured or semi-structured. Unstructured data would include things like photographs or even video. And semi-structured data would be things like output from sensors, or like Internet of Things devices, where you've got a bunch of robot-style devices that are gathering information from, and each one logs its information or the metrics that it is monitoring in the format that the developer that wrote that particular line of code thought made sense. It might be consistent within a single device across the different things that it monitors, but if you look across many different devices, you're going to have a lot of variety. And so we would call that semi-structured. An example would be if you had a trucking company. You might have GPS data, tire pressure sensors, fuel consumption rates, and maybe even facial recognition to do pre-sleep detection warnings. And then all of this data can be tied together to be useful, but it does represent a lot of variety. So the classic approach to data processing where you have very well structured data that goes into a database. And in that classic model, in order to process that data, it has to be pulled across to an application. The application may be running on an application server that's dedicated to the task, or it could be running on desktops. But in either case, there is some inherent limitations to this model. One is the size of the database. So the software may have a set of limitations, and even if the software doesn't limit how much data can be stored in it, then there's a question of how big of a machine can you buy to hold that data. And if you get beyond the size of what's reasonable to store in a single machine, then you can look at using some very expensive solutions to scale laterally, such as Oracle RAC, where you distribute the database load across multiple database servers, or doing some artificial mechanisms where you split up your databases so that the table space is spread. So maybe all of the records that start with A are on one database server, all the records that start with B are on a second database server. And while that can work, it introduces a whole nother level of complexity to the management of your environment. Also, we tend to use expensive disks in SAN-style storage for fault tolerance and high availability. And then when the data needs to be used, it has to be pulled across the network. If there are any changes that are made, it has to be pushed back across the network and written back to the database. If we look at the big data model, we have a change of paradigm. Now, instead of moving the data from the database to the application, we distribute the data across all of our big data nodes instead of having it on just a couple of nodes. And then, this is really cool, we take the application and we move it to the data. And so then you don't have to move the data across the network, and the analysis happens right there where the data sits. Now we'll take a closer look at this in a minute, and I think when we do, you'll have some light bulbs go off in your head. But let's go ahead and dig in a little bit deeper here. How do we store data in a big data environment? The Hadoop file system is designed to operate on inexpensive disks, and it has fault tolerance built into it that allows it to distribute the data across multiple independent disks, multiple nodes, or even across several nodes in a cluster. It also is aware of where the data is so that it can tell an application that wants to access the data. So let's take a look at this node here. We've got one node, and it has one chunk of data indicated in yellow, and we've written that chunk of data to our HDFS file system. Now with only one node, what happens is it takes that chunk of data and replicates it to a second and then a third disk within the same node. So at this point, you can lose any disk in that node and still have all of your data. For that matter, you could actually lose 2 disks and still have all the data. And then HDFS would take care of replicating that chunk of data to 2 other surviving disks. So what happens if we've got 3 nodes? Well, HDFS is geospatial aware, and so it will prefer to replicate that block of data to a different disk on a different machine, and then the third chunk of data to an independent disk on a third machine. At this point, you could lose any one machine and still have all of your data, or even 2. So what if you actually have 3 racks of machines? In this case, HDFS knows which rack each machine is in, and a rack can be a failure domain. What if the power goes out to an entire rack based on where it's connected to the power feed? Well, with the data replicated by HDFS across, when it knows that it has the ability to replicate across 3 different disks in 3 different nodes that are in 3 different racks, it will do so as to eliminate as many failure domains as possible. And in this scenario, we can even lose 2 whole racks and still have access to all of the data. One of the common thoughts that go through people's head at this point is, well, gee, that's a lot of redundant data. Isn't that expensive? Well, the first part of the answer is because we are using inexpensive SATA disks that are in the local nodes themselves rather than expensive high-speed disks in a complex SAN environment, the cost per gigabyte of storage, gigabyte of raw storage, is much lower. But here's the other part that is really cool. You'll notice that these data nodes also have processors on them. Each of these nodes is not just storing data, it's also able to run applications to analyze the data. So if you've got a chunk of data, if you've got an application that needs to analyze a chunk of data, then it can talk to HDFS and find out where does that data live. And now it's got 3 different nodes it could choose from. So let's say it takes 60 minutes to analyze the data on a node. Well, check this out. What if the application was able to split itself into 3 and do the first third on one node, the second third on the middle node in rack 2, and the third third in that node in rack 3, you could analyze the data in 1/3 the time. So instead of 60 minutes to analyze that chunk of data, it now only takes you 20 minutes. So let's take this one step further. Now we've added a second chunk of data, purple data. Now with this purple data, if we have an application that needs to analyze both the yellow and the purple data as part of its job, it now has 6 machines it can distribute the work across. So it can actually get that done in 1/6 the time. So that 60-minute job running across 6 nodes now only takes 10 minutes. That's pretty cool. Who uses this? Who can take advantage of it? And it turns out that it is such a flexible framework and is so open to adaptation that virtually every industry can leverage it. And that is in fact what we're seeing. As a matter of fact, in a recent month, I was speaking with an internet service software provider out in California, an investment bank in the Northeast, and even a major auto manufacturer that are all using big data solutions. And many of the high-performance computing solutions that we've sold over the years have included a big data component. And that is getting more and more attention and is becoming increasingly important as part of research computing environments, to include the ability to run big data workloads on what would be a classic HPC solution. There's been huge growth in the big data space. As a matter of fact, I love this statistic here on the top left. 90% of the data that exists today did not exist 2 years ago. Wow. And the rate of data growth is increasing with people taking all these pictures with their smartphones. I don't know about you guys, but whenever I do an expense report, or when I'm incurring expenses, I'll just take the receipt, I take a picture of it, throw the receipt away, and all of that turns into big data. And that data has value that goes beyond simply being able to do an expense report. And for the companies that are finding ways to take advantage of that additional value. They're seeing return on their investment quickly, and they're wanting to buy more. So, according to IDC, at the end of 2013, they estimated that the big data market demand worldwide, this is products, services, hardware, everything, would be about $16 billion in 2014. Well, at the end of 2014, they estimated that it would be $125 billion in 2015. So that's pretty significant. That's pretty big. I guess as Donald Trump would say, that's huge. So let's take a look at some of the software that makes up a big data software stack. I think we have to take a look at the fundamental idea here that we've got data represented by the hexagons on the left, and then being able to do analytics on that data of all different kinds is what leads to actionable insights, which is what's driving the interest in all of this. So how did this all get started? Well, Hadoop was, there was a paper that was written by Google back in, I think, 2004 that was them exploring how they were going to handle these massive volumes of data that they were pulling in with their search engine business. And so in this white paper, they described a method for distributing data amongst many independent nodes, mapping that data so that they knew where it was, and then having applications that could use those maps to execute where the data lived, and then take the results or the reduced set of data that had the answers to the queries or the results of the analytics and bring it back as the end product. And that model has been called map reduce. You map the data out, you provide the map to the application runs across the nodes where the data is and brings back the reduced data set or the generated data set that represents the analytics. And this was, although it was just a white paper produced by Google, and then they later created internal code that they have used to operate this internally, it wasn't until Yahoo got a hold of this that they actually created some open source software that was based on that model, and they called it Hadoop. Hadoop, by the way, was the name of a toy elephant that one of the original creators, it was his daughter's toy elephant, so they called it Hadoop. Hadoop is a framework that includes many different components that provide different services that all facilitate this MapReduce methodology of distribution of the data in mass and providing applications with a way of getting to it and executing on it. Spark, which you likely have heard of, is, I mean, this big data thing is still relatively new, but it's growing in such popularity that Spark is already what you might call a next generation framework. And it doesn't provide all of the same things that Hadoop provides. As a matter of fact, it is a part of the same software project foundation, the Apache Software Foundation, and it provides the framework for running applications, but doesn't recreate a lot of the other things like HDFS and some of the other infrastructure, but is intended to work hand in hand with Hadoop. So for applications that are able to be executed within the Spark framework, you can see as much as a 100 times speed up. So they can run 100 times faster in Spark than the same application running in Hadoop. And As of the time that I put this slide together, Spark has been run on clusters of up to 8,000 nodes, so very scalable. If you're putting together a big data solution and you have lots of choices, which you do, as you can see here, how do you know what to choose? There's lots and lots of software available that make up parts of a big data solution. One way to think about this is email clients. You've got an email client on your phone, you've got an email client on your desktop, and you've got an email client in your web browser. Now they're all able to access the same email, so they provide the same basic functionality, but each of them does it a little bit different and is optimized for a certain use case. So the same is true for a lot of applications that tie into a big data environment. And how do you choose? And which ones are appropriate and how do you manage it all? So this is where the big data distributions come into play. I think that a good way to look at this is with a Linux distribution analogy. With Linux distributions, you have, let's say, Red Hat, you have SUSE, you have Ubuntu, and each of these distributions is based on the same software, essentially. It has the ability to choose from the same open source softwares. They're all running the same kernel. They're all running the same basic libraries, but they may be choosing different versions. And so each of the Linux distributions chooses the versions of the softwares that they believe worked best together, the specific choice of applications when there's more than one that can do the same function, and then they apply their own systems management methodology, and then they wrap it up with their own services model for supporting these systems. The big data distribution landscape is the same way. Now let's take a look at big data hardware. What does it take to run a big data solution? Hadoop was designed to run on low-cost servers and is designed with fault tolerance built in at the software layer. That said, having Lenovo servers with the highest of reliability definitely makes life easier, because when you're dealing with large numbers of systems at scale, the statistics of mean time between failure can make a big difference in how much effort you have to put into managing the system on an ongoing basis. So within a Hadoop cluster, you have two key kinds of nodes. You have manager nodes, which are responsible for keeping track of where the data is stored across all of the data nodes, for telling applications how to get to it. And then the data nodes are the ones that do the heavy lifting. The data nodes are going to be the most plentiful kind of node in the solution, and they're the ones that store all the data and do all the analytics. And of course, as a Lenovo best practice, we recommend deploying a big data solution with a cluster manager node or a systems management node that can be used to control all of the other nodes in the cluster, all of the manager nodes and the data nodes, from an operating system deployment perspective, remote access to consoles, and hardware level manipulation, power on, power off, and things like that. Let's take a look at an example solution architecture. We have our data nodes with number 1 on the left, and we'll have several of those. We'll have a handful of management nodes. Usually 3 is the magic starting number for management nodes. And then we'll have a couple of rack switches. We'll generally have one that is for out-of-band management per rack. This would be like a 1 gig switch and a Lenovo G8052. And then we'll have 1 or 2 10 gig switches, the Lenovo 8272 is the ideal choice for that. And in cases where network bandwidth is particularly important, we can also deploy solutions using InfiniBand. So when it comes time for expansion, one of the really cool things about a big data solution is you don't have to reconfigure the environment in order to take advantage of the new nodes. You don't have to change the way that you tell the applications to run across the system. You simply plug in the new nodes to power and to the network, and then you tell the management nodes, here are some more data nodes that you can start sending data out to and have applications run across. And this is a zero downtime operation. So what does Lenovo have to offer from a big data perspective? So of course we have excellent hardware. Lenovo servers have achieved a remarkably high reliability rating and are very well thought of in terms of customer satisfaction. And this is a ranking that is not new. You can see that we've been hitting this #1 in customer satisfaction for servers for the last 6 out of 7 quarters as of October of 2015. Our 3650, this is the X3650 M5, is our flagship big data node. Data nodes are typically a 2U, and the reason for that is because of drive density. So with this node on the top, these are both X3650s. The node on the top has a different drive layout, allows you to get 26 2.5-inch drives into that single node, and you're only going to notice 24 of them there in the front. There's a couple more drives that we can install in the back. The node on the bottom is also a 3650 M5 with all of the other components in the system exactly the same as the one above, but with a different form factor for the drive storage. So the one on the bottom is actually our most popular layout for big data because it hits the sweet spot in terms of capacity and performance with the large form factor drives, and we can actually get 14 of those in there. Again, you're only going to see 12 in the front, and there's another 2 drives in the rear, and a pair of 2.5-inch drives for booting. As you saw from the slides earlier on HDFS, where we had the yellow chunk of data, and it got replicated to other independent disks, well, in such a scenario, you don't really need a RAID controller in order to achieve fault tolerance. So does it make sense to have a RAID controller anyway? And the answer is no, actually. I mean, maybe it's useful to have a RAID controller for the operating system disks because it's still good to ensure that you can boot the system. But the system can continue to be functional even after the loss of individual data disks. And it turns out there is a performance penalty that is imposed by having the RAID layer on top of the disks. For the data disks, we actually use a non-RAID SAS controller. All of the disks in the operating system present themselves directly as independent disks. And of course we have the 8272 switch on top, and you'll notice that it has on the far right side, it has 6 40 gig ports which allow us to connect multiple racks together or even uplink to a corporate central switch and still maintain very good bandwidth. On the bottom, this is a couple of examples of layouts for the X3550 M5 that we would use as management nodes. The management nodes don't require as many disks as the data nodes do, and we do still use RAID in those because they are going to be holding data that is not necessarily redundant in and of itself from databases and other management components that we want to provide a file system level fault tolerance for. So when you order a solution, a big data solution from Lenovo, we can take your requirements as a customer, design a solution to match those requirements, manufacture it in our facilities so that it is stress tested, and we even do things to provoke infant mortality of components such as DIMMs, which is good for us and it's good for you. It's less expensive for us to replace a DIMM that fails on the manufacturing floor than it is for us to send a guy out to your site and replace it in person there. And it's better for you because the system is more reliable. Additionally, it can be delivered in rack with all of the equipment already mounted, cabled, with Cat5 Ethernet cables cut to length, everything nicely tied down and ready to go. Where all you have to do is roll it into place on your floor, plug it in to power, plug it into network, turn it on, and then it's ready for our professional services team to deploy your solution. To facilitate the design process, we also have reference architectures where we have worked closely with right now 3 of the key big data distribution vendors. IBM for their Big Insights for Apache Hadoop solution, MapR, and Cloudera. All 3 of these are Hadoop-based solutions, and we hope to have a Hortonworks-based solution in the near future. Part of the reference architecture includes an architecture brief, which is, you can think of it like a data sheet, a 4-page data sheet for a big data solution, and it represents a snapshot view into the full reference architecture. The full reference architecture is more of a red book style document that can be anywhere from 30 to 60 pages long and goes into in-depth details for how a solution is architected, best practices, why decisions were made for everything from networking components to description of tuning parameters, and even documenting ways that you can change the architecture to optimize for high availability or for cost. And of course, we can architect a solution specifically to meet a customer's requirements. And we generally start with our reference architectures and then make modifications based on those so that we incorporate the best practices from those reference architectures. And then, of course, we're able to deliver those fully assembled in the racks. We also offer professional services. Our professional services team can provide deployment services and also managed services. So deployment services, once your system is delivered and the hardware is physically in place, our professional services team can come out and deploy the operating system, make sure that all of the components are integrated to your local requirements, IP addressing, network standards, things like that. Provision the system with your Linux distribution, and then deploy the big data software distribution on top of that, bringing you up to a running big data environment that's ready for your work. And of course, we also offer managed services, which includes 24/7 monitoring on premises, and even the ability to host your solution in one of our data centers if you prefer. Thank you very much. And once again, this is Brian Finley with the Lenovo Big Data Center of Competency, and hope to see you soon. Bye for now.